Hello everyone, for those who don't know me, I'm David Morgan. I am the Surface Analysis Manager at Cardiff University, and I'm also the Technical Manager for the UK National Research Facility in X-ray Photoelectron Spectroscopy, Harwell XPS, which is based down at the Harwell campus right next door to Diamond. So today I'm going to talk about the classic Beamson and Briggs degradation index for polymers. And how it looks, or how we can apply it, or should apply it perhaps, to modern spectrometers. So in terms of anything from Axis Ultra to even, I'm sorry, you're going to see data from thermal systems. Control yourself. I know, there's going to be a riot. I know. So quickly, the NRF, we have, as I say, we give access to academia and industry to a range of XPS instrumentation. We have obviously Axis Ultra at Cardiff. We have the Axis Supra at Harwell. We've also got thermo systems. Again, we won't take too much. And we also, down the road, give access to the Omicron HAPS phase gap liquid gallium system and NAP XPS systems via links with the Royce Institute. And of course, we give access to all the ancillary techniques. You can get ISS, REALS, UPS, Raman, and we also just introduced lab-based X-ray absorption spectroscopy as well. But we're always there to train, for training knowledge, facilitate and collaborate with research. We're community focused, and obviously want to develop techniques, and we're developing more electrochemical things. Now we've upgraded the Supra with the electrochemical stage, and also internal flow cells for in situ work and so forth. But anyway, what we hear about is plastics, polymers, Beamson and Briggs. So we want to understand polymer degradation for many reasons. These are just a few of them. And it is to understand that surface chemistry. We want to understand how these plastics, these polymers interact with chemicals, how they change with temperature. What happens when they're exposed to natural environments, to waste streams? What happens when in the sea? We think of microplastics, etc. How do they interact with human tissues? So biocompatibility, stents, catheters, and so forth. We also therefore have a bioincompatibility, perhaps, when we look at microplastics and we talk about these degraded or eroded materials. And obviously there's environmental concerns there as well. But regardless of what aspect you look at these polymers and so forth, we want to evaluate how the surface or the chemistry or the polymer is changing, and we typically do that by XPS. But what we want to do is do it with XPS and do it right. So we want to get minimal artifacts. So the impetus for this study came many years ago, and it stood, here we go, Kratos Users Meeting 2018, if I got the date right, and was followed up at the KZIA 19, where we showed, I showed that if you looked at chromium systems, it was known, and Kratos, you guys use it in your sales literature about degradation of or certainly have about chromium compounds. We showed that on the electron-only neutralizations, that's from my Ultra system, we can see actually bulk chromium 6 oxide has some reduced states in it to start with, but regardless, it stays there. You always have this fairly constant ratio of chromium 6 to chromium 3. But when we've done on the thermo system, which uses dual neutralization, you can see that the reduction is much faster, and you get to this almost sort of 50-50 within sort of 30 minutes or so of analysis. Now, depending on what you're looking at, that can be quite significant. But more importantly, what we showed was, even though that thermo system uses microfocused X-rays, the X-rays had little or no effect on this reduction. If you just sat the neutralizer only on it with no X-rays whatsoever, the neutralizer was the cause of a significant amount of the reduction. And we primarily studied inorganics and moths and these type of materials then. Then recently we've looked more at more organic systems. So this is a polyelectrolyte, and we can see that in this case, on that particular system, we've only got the thermo data here, we can see that the X-rays and neutralizer basically have the same effect. And we can kind of see these highlighted percentages, 14 0.6, 14, and the sum, if you looked at X-rays and neutralizer, is about 23. So almost like a doubling of an additive effect there. So again, we have to be careful on what we analyze, and we kind of know that ourselves from what we analyze with the wealth of experience we have in XPS analysis. But then it got me thinking, what about soft materials, organics, and especially polymers? And the first place you go to when you think of polymers is Beamson and Briggs, the Scienta ESCA 300 database. And we probably all, most of us, if not all, have a copy on our desks or as a PDF at least, acquired from somewhere. But I have both. But anyway, regardless of that, within that book, you will see plots such as this. And these are exemplar plots taken just straight from there for chlorine on the left-hand side, or some chlorinated polymers and fluorinated polymers on the right-hand side. And you can see you get the plot of the atomic ratio at time t, reference to time 0, over a given time. And this gives you there the so-called degradation index. Okay, and you can see that all polymers behave differently and have different degradation indexes as shown on the y-axis. But there are some issues with this, and some people might want to disagree, but these are how I particularly see them. So again, let's just consider this chlorine degradation index at the moment. The index Beamson and Briggs came up with, the value of their degradation is after 500 minutes of analysis. Okay, and we'll see that's no good. And it's rounded up to whatever value you get is rounded to the nearest 5%. But some of the issues in this is, there we go. The reported index is after 500 minutes. Our analysis is typically below 60 minutes, probably 30 minutes, depending, especially for polymer. You can fly through these. There's some variation in experimental parameters, a number of scans, use of masks, some contamination in some, but they're quite upfront and open about that. The X-ray power, 1.4 kilowatts. It's a very powerful source, but anybody who knows about that system understands those reasons and so forth. Issue of analysis area, what's the spot size? How much is illuminated? And it's not quite clear. But the book also states that some the index is rounded up. For some, if you actually do the graph and look at the values given, some are rounded up and some are rounded down. Okay, there's not a big difference, but 5% error at least. And there's probably other little bits and pieces that I've missed. So indexes over that time frame, probably not the best. And we'll see how that pans out. Of course, we think degradation, put my sort of BSI hat on, or ISO hat if you like. There's international standards on degradation, how we can should do these experiments, and how we can sort of, if we do observe degradation, how to look at those samples and sort of calculate back to the original concentration. And again, we've just got a little schematic there of the of one of the Beamson and Briggs plots, but the ISO standards goes up to about 30%. Any more than 30%, don't try and sort of extrapolate back if you like. But really, our analysis is in this sort of time frame here, within that 60-minute window. And you can see, if you think of this as a rate plot, the rate of change within that first hour of analysis is much different to further along. So you're going to have different kinetics, and therefore those kinetics will affect degradation and the rates and so forth. So experimental wise, here we are. Here's the two different types of systems, and they are totally different in terms of how they do the XPS, if you like. We've got the Ultra DLD, but we've seen similar results of the Super as well. So we're treating them as one here. But basically, we're talking very simply broad X-ray spot, electron-only neutralization, a lens-defined analysis area, and we're using an X-ray power of 144 watts. The K-alpha, micro-focused X-rays, dual neutralization. The analysis area is defined by the X-ray spot, this micro-focus, and 72 watts max power, so it's operating at its maximum mode. But we've obviously used 144 watts with the Ultra, just to try and sort of account for a doubling of that effect or something. To at least try and scale it to with no rhyme method or madness. So what do we see? quite different profiles. Well, first of all, note on these two plots, if we do these for the fluorinated polymers, just PTFE, PV, polyvinyl difluoride, and PVF, we have different, you can see from the shapes, the kinetics will be different, the rates are different, and also, as I say, note the differences in the Y scale. The axis data, if you take PTFE as an example, very linear, lovely, straight. And these aren't deviating too far off that, either the PVF and PVDF. Whereas you can see quite significant curvature in the data from the thermo system. And again, as I say, the y-axes are different than here, so I apologize for that. But you can see after 500 minutes, we've got 75 degradation there, 75, so 25% degradation, so index in 25. To get down to PVF, in 400 minutes as opposed to 500 minutes, it's 30%, sorry, 40% degradation. So you can see the significant differences. And if these are different here, these initial rates are different. So, and there we are. You can see the time difference there as well. There we are, for chlorine as well, sorry. So there's the chlorine, again, seeing similar behavior there. So if we use chlorine as, or PVC, as the sort of ubiquitous degradation polymer, we've all seen studies on that. Indeed, there's been VAMA studies involving PVC and so forth. And again, we're looking at the thermo data here because the Kratos system, as I say, is a broad spot analysis. But you can use any PVC, doesn't matter, it doesn't have to be perfect. The quality can be pretty poor, as we've got one here. This commercial unplasticized PVC bought from Goodfellow, but you can see it's got some unsaturated hydrocarbon, a little bit of oxygen. But the degradation profiles are the same regardless, and this has been shown in the literature, Don Bear and so forth. And we can see X-ray spot has an influence, and that's not surprising if you go in from a 400 micron spot down to 200 micron spot, but keeping the photon intensity, the power into that area the same. It's got the scale, or should probably scale somehow. And we can see there's a doubling of the rate, the difference in rate, and we can see the kinetics in those are quite different if we do a log plot. But again, as I say, it's not too applicable to the axis system because the type of spot. But earlier on, I talked about the neutralizer in terms of a thermo system. And what we see, and we've seen the degradation that can do for the polyelectrolyte, and also for the inorganics that had a significant effect. Actually, it has a much smaller effect on these polymers. It's more micro-focused X-rays which have the issue. However, there is an influence from the neutralizer. And we don't see this as greatly as we just do the electron only. So it has to be the argon ions as well as the electrons in there, because we can see if we change our extract voltage on our neutralizer from 40 volts to 30 volts, we can see that there's a difference, again, about double of the rate just from the neutralizer. Now, that's not a big influence because, as I say, or big problem perhaps, because, as I say, this is our data curve for just the X-rays only, or just doing the XPS with both neutralizer and the X-rays on, or indeed the green triangles. As you can see, they're slightly offset. That's just where we've had the X-rays on, moved away, neutralizer back on, moved over, and analysed in that sort of mode. But we can see literally, if you have a student using your system, or a lazy technician or something like that, and then they turn on the neutralizer, try to optimize position, thinks, oh, I'll just leave the neutralizer on, it's fine, I'll go have a cup of coffee. You can see within that coffee break, which should usually say be 30 minutes, probably more 180 minutes. After 120, you can see you have 30% degradation just from the or 30% reduction just from the neutralizer alone. So obviously, we know that these neutralizers can damage things, just the electrons only alone. But regardless, you can have that influence. So dual neutralizer not very significant. Mostly, unlike polyelectrolytes or the inorganic materials, the additive effect is small here. It's totally the X-rays. But still, we can see just from this plot alone, just looking at the chlorine to carbon ratio in this case, doesn't matter how you present this data, whether it's as the degradation index, just a simple ratio like that, or as a log plot, whatever, the data will mean the same, and we have this sort of linear region in that first 30 minutes. So we need to minimize to below 30 minutes. And of course, this has an effect for small spot analysis. But let's have a look. Let's get back. Let's stop talking about thermo. We've had enough about them, although you guys are probably loving it in some ways. But let's have a look. Let's just put comparison of degradation indexes. So B&B, Beamson and Briggs, 500 after 500 minutes. And here's the data from the K alpha in the blue line and the Axis Ultra in the green line. And we can see in all cases, the Ultra, and let's say the Super gives us very similar numbers within error, are much better. Of course, we're still talking 500 minutes, a crazy amount of time for data analysis. So let's actually put on the data where we just do it up to, let's say, 60 minutes. Let's take that as our cutoff. And we can see I've also put on, extrapolated the Beamson and Briggs value there for 60 minutes. So in red, quite small. So you can see for PVC, they say the degradation index is, let's say it's about 25. After 60 minutes, it's what, about 5%. Well, the Ultra, there we are, 10%. So it's within our sort of range. And again, we're saying we're doing these analysis much quicker. But again, the other systems, where are we? The blue line, again, over 40% degradation in that case. So absolutely pick the right system if you've got access to multiple systems for the job. If you've only got a critical system, fine. You've got nothing to worry about. But there we go. So damage rates are more manageable under up to 60-minute irradiation under default conditions. But you can see these can be giving you potential issues if you're using another system or have any sort of microfocused X-ray sources or whatever else for things like angle resolved, where you're constantly looking at that same point. Yeah, you turn in, but it's still illuminating that area. And that's something we saw with the fluorinated polymer. By the time we'd gone from 0 to about 30 degrees, the polymer had gone off the surface. Again, that's something that sort of piqued the interest in this. As I say, this is true regardless of manufacturer and whatever else, but we've got differences in distances of the X-ray source, sample, monochromator design, X-ray power, whatever. There's a lot of variables, but we have to. Beamson and Briggs is taken as law. Is it? Well, in some ways, yes. In terms of a lot of the samples, we follow that plot, especially the halide polymers. But we can see greater degradation in those sort of timeframes. But we need to, as users, and have to be aware of that. But there is a difference, and we haven't run these on the Ultra yet, so it would be interesting to see if it stands true before the, let's say, carbon oxygen or carbon nitrogen polymers such as PEG, PVA, PBG, and so forth, PVP. There is the order of degradation changes for those particular materials, and that needs a little bit more work to look into. But really, what we should all be doing is this little bit of work, which is, again, cursory looks at the glances at the literature, can't really find much about it. And Don Baird had even forgotten about this work that he done, the PTI, the photon threshold index. So he was quite pleased when he heard the talk in Limerick, but and jogged his memory. But basically, you can see if you measure PVC in your system under whatever your default conditions or whatever, you can then take your Beamson and Briggs index and work out your PTI for your system. And you can see when you plot them, this is for 10% of degradation of PVC. Okay, and you can link it with the Beamson and Briggs index in this paper. You can get a plot such as this. So you can see for the chlorinated and fluorinated polymers we have here, actually the thermal system in red, quite clumped together. So you can see how damaging those are. And that does show, what we're seeing there is reflected in those plots that we've already seen. But again, we've almost got a very nice linear sort of plot there in terms of the PTI for the for the ultra, with PVC being the most easily reduced and PTFE actually being the least easily reduced in this case. That was confirmed by both plumber's tape and a PTFE rod as well. And this is good because if you make a change to your system, new anode goes in, whatever you can think of, start running a different X-ray power, just measure PVC again. You can easily change, update those numbers because you're only just doing it relative to that one PVC sample that you've measured. So just to sort of conclude, just to summarize, Kratos is still doing it right. We're still using electrons, just stick to them. Electrons are good. We can neutralize with them and we can record spectra with them. It's great. And yeah, illuminate the areas seems to be better, and you can get that selected area. Keep it with selected area. For the polymer analysis, the neutralizer in a dual neutralizer system seems to be less of an issue unless, as the data we saw, you had a student who leaves it unattended and takes long coffee breaks. And unsurprisingly, it's the microfocus X-rays that have a greater issue there, more influence there. And again, Kratos systems damage effects are much slower. We can't stop these effects unless we start cooling samples and sort of reducing that time frame, but it's going to happen. It's the nature of chemistry. And again, the Beamson and Briggs index, yes, the order generally holds true for regardless of spectrometer, but with some exceptions. It's not ideal for most lab-based spectrometers as the damage is greater. So we really need to be looking at having an index which is up to sort of below 60 or 30 minutes, where the degradation tends to be limited to 10% in most cases. So recommended degradation index should be made for T max of about 30 minutes. And again, use a PTI for your own systems, or if you have multiple systems, to allow you to pick the right tool, the right instrument for the right job. And there we are. Thank you very much.